So our goal is to decide how much is it going to warm up by lunchtime, by next weekend, maybe 30 years from now. That's the main goal of thermodynamics. If you look at the temperatures at any given time, any given location, you can often see that there's a huge range. Here are today's temperatures in Central California. They range from the 50s and 60s along the coast. That's what this number is, 59, to the high 90s inland, 95, 97, 97, 94. So to figure out what the temperature is going to be in 1 hour from now, let's say, is maybe a different thing here from over here because of the different starting temperatures. So when we ask what the temperature is going to be, we need a new way of answering that question, and that involves something called an air parcel. Air parcel. So an air parcel, as you might guess, is a parcel of air, and we're just going to focus on that single air parcel to figure out what's going to happen to it in the future. So we can start by drawing a picture of an air parcel. Looks like this. Inside the air parcel is air, and for the time being we'll assume that it's dry air, because as soon as we start adding humidity, things get more complicated. So we'll do that later. So we have an air parcel, and we're going to ask what happens to various thermodynamic properties inside the air parcel. Now, there's a couple of things that we want to think about with the air parcel. Let's try doing a red thing here. In theory, in the real atmosphere, there's no such thing as an air parcel with a skin. And so you can have a constant flow of outside air into this region and inside air out of that region. So we might call this an open air parcel because the airflow can go back and forth. But that turns out to be more difficult to study. So we'll get rid of that and go back to having blue, and we'll think of this as a closed air parcel where the air that's already inside stays in there and never leaks out and doesn't exchange with the outside air. The other thing we have to think about with our air parcel is the size of the air parcel. So let me show you a couple of things that won't work. Suppose you take a classroom. So 10 or 12 feet tall, 20 by 30 feet long. Maybe we can have a door. And over here, maybe we've got some windows. And inside, you've got students, computers, teacher, you name it. If we were to go around here carefully and measure temperatures, we might find that it's 75 degrees in this corner. Maybe it's 76 over here by the window. It might be 73 down here at the floor. And over in the corner where your lecturer is standing, emitting hot air, blah, 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 you might find that it's 78 degrees. So the problem with something this size is that there is no one value of temperature that works for everything, and there won't be the same value of density that works for everything either. So the air parcel has to be smaller. So what works for me is to think about a kid's party balloon. So here's a kid with long arms, yes. And there's a balloon with a string on the end. And there's the kid. think about a kid's party balloon that's going to be maybe 6 or so inches across. Hopefully, there'll just be one value of temperature inside, and there'll just be one value of air density inside. Okay, so now thinking about our air parcel, what kinds of things might we want to know about the insides of the air parcel? And those things would be, the most obvious one probably is temperature, running out of space, density, and pressure. These are three things that we spend a whole lot of time thinking about when it comes to the atmosphere and trying to predict, especially temperature and pressure. Density we pay somewhat less attention to, but you'll figure out why later on. And then maybe later on too, whoa, the whole thing is moving. Later, I must be touching a button I don't know about. Humidity. So these are three things that we need to understand and figure out how they work inside the parcel. So let's start with temperature. When you pull up a weather app to look at the forecast, it's always going to tell you what the temperature is going to be. So this may be the most important thing. So let's think about our air parcel, and let's think about our molecules buzzing around inside. And that's exactly what they're doing. They're not stationary. They're buzzing around in random directions, colliding with each other, bumping into the walls. I could do this forever, quite obviously. And I think intuitively it makes sense to say that as it gets warmer in this parcel, the molecules move faster. Okay, so let's do, this is going to be an action figure now, okay, a movie. So here's a cold case, and the molecules are really slowly moving around because it's cold. And then here's a warm case. It's intuitively straightforward to say that the molecules are going to be moving around much faster because it's warmer, and that additional warmth means they have more kinetic energy. And it's kinetic energy that is the thing we experience as temperature. Kinetic. Let's get rid of this. Energy. So temperature is really a measure of the kinetic energy of the molecules inside of our air parcel. And if the sun were to then come along and shine on the air parcel, well, you would think that it's going to provide more energy to the molecules. They're going to buzz around faster with more kinetic energy, and you'll get more temperature, a higher temperature out of that. Maybe the next thing we should talk about is density. Yeah, that doesn't look like a D, but it is. So density is just, that doesn't look like a circle either, but it is. Density is simply a measure of how much of whatever substance it is, in this case, is present in our air parcel. So this is less dense, the blue example, and then just to be lazy, I'll superimpose some more molecules on top of this to indicate the more dense case. Hopefully this is a familiar concept that you've heard about from back in high school chemistry or high school physics or something. So this is more dense. And it turns out that some smart people back in the day figured out that there are connections between temperature and density inside this air parcel. And we'll look at those in just a minute. Okay, the third quantity that we want to look at in terms of what's going on inside our air parcel is pressure. Air pressure is something that we pay a lot of attention to in weather forecasting. Whoops, and here's an example. Here's today's weather map. And no doubt you've seen weather maps with the letter H and the letter L written on them. These stand for areas of high pressure, low pressure, high pressure, low pressure, and high pressure. And if you didn't already know it, high pressure regions are fairly quiet and inactive. Low pressure regions is where the action is in terms of weather. So this is sort of large scale pressure. What we're interested in is pressure within our air parcel. So let's look and see how that works. So let's suppose that we have some molecules in here, and some of those molecules are going to be, in effect, bumping into the skin of the parcel from the inside, and that is experienced as pressure. And you might reasonably expect that if the molecules are moving faster, they're going to exert more pressure on the parcel, and vice versa. So that, let's see, if you let them, the internal pressure might push the boundaries of the parcel outward, and the parcel would expand. The other possibility, of course, is if there's air pressure from the surroundings, which is stronger, and oftentimes we let the lengths of these wiggly arrows represent the strength of the pressure and so forth, well, that might compress the parcel. Okay, so air pressure is a sense of, let me get rid of that magenta line. Air pressure is a sense of the pressure that the molecules inside are exerting on the skin of this imaginary parcel. Okay, one final thing, and that is the notation that we use for these quantities. So for temperature, we use the symbol capital T. Capital T always represents the temperature. For air pressure, we use the symbol little p, and oftentimes editors will try to capitalize that, but no, we use the symbol little p for air pressure. And finally, for density, we've run out of letters, so now we have to use a Greek letter, and let me see if I can find that. We use the Greek symbol rho. And where is that? Greek rho. I've got too many. Okay. You need to get used to drawing the, whoops, that's not working properly. Drawing the little p as different from the Greek little rho, because it will be important for me to tell what you're talking about.